Swayam Prabha. Digital India. Educated India.
Welcome you all to this lecture of flow through porous media. We were discussing about immiscible flow, and we had talked about this movement of Buckley-Leverett front in our last lecture. So, I will conclude this discussion on Buckley-Leverett front theory, and then I will move to other topics where we have gas phase present and there is a vapor liquid interaction term. So, what we were discussing at the end of what we discussed before about this Buckley-Leverett method is that we saw that this dFW dSW on one hand is this quantity, and similarly dFW dSW is also this quantity, and these two have to be satisfied when Buckley-Leverett front reaches the outlet. So, this we just put this as SWF. And so, we made a geometric construction where we had FW versus SW curve already known to us, because FW is basically QW divided by QT, volumetric flow of water divided by total volumetric flow, where QW was KR by mu for waiting phase divided by KR by mu for waiting plus Kr by mu for non-waiting. So, since Kr is a function of saturation, so Fw would be a function of saturation, and if someone takes correlation for relative permeability, that is Kr versus saturation for water phase and oil phase, and put this in there. So, Fw versus Sw curve takes this shape. And to satisfy these two conditions of dFW, dSW at the when the Buckley-Leverett front reaches the outlet, one has to draw tangent to this curve Fw versus Sw curve from the point here, which is Swi, and wherever it hits this Fw is equal to 1.0 line, we call that Sw bar. So, this simplified the process much, and so beyond this point what we said is that production of oil from this porous medium would be so this is Rp as a function of pore volume. This is, if we are starting from 0 here, Rp production would be then 1 minus SOR minus SWI, because originally the oil that was placed or oil was in place is 1 minus SWI, and out of that SOR fraction has to be left out at the end. So, this is the end point, and then we find that here the Vp is the pore volume, total pore volume produced, that is water plus oil, which is equal to total pore volume of water injected, and total pore volume produced would be only oil until some point which we referred here as star. So, till this point this curve would be a linear straight line. So, this star refers to breakthrough of waiting phase at the outlet, So, beyond this point both water and oil will be produced. So, that is why the curve is deviating from the straight line, and so till this point cumulative waiting phase injected equal to cumulative non-waiting phase produced. At this point SW at the outlet is SWF, average saturation at this point, that means I have the plug, porous plug, and the front has reached. So, this is the this is 1 minus SOR and this is SWF. This is how the SW versus X curve looks like. So, then the average of these all these saturations, which is let us say SW bar. So, that SW bar refers to average saturation here, and the oil produced at any time would be the SW bar existing in the porous medium minus the original SWI that was in place. So, that is the change in saturation. Average saturation to start with was SWI, the interstitial saturation, and after some flooding the average saturation became SW bar, and this difference in saturation in water happened because the corresponding amount of oil was expelled from the porous media. So, from there one can find out what is the total oil produced using this relation of SW bar minus SWI. So, this whole exercise refers to, I think, these plots here. First of all, one has to generate this FW versus SW curve based on the relative permeability versus saturation information. Relative permeability versus saturation, there would be correlation available. One such correlation was Corey's relation. Otherwise, this correlation has to be developed for an unknown porous medium and for an unknown wetting and non-wetting phases. So, this curve has to be developed, and then one has to draw from SWI and find out what is SW bar, but this SW bar is at the time when Buckley-Leverett front has reached the outlet. Okay. So, that is, so these point, so this at this point how much oil was produced would be SW, this SW bar minus SWI. So, that means this distance, if we draw the vertical here, this is SW bar from here and this SW bar minus SWI, that would be the amount of oil produced till that time, and till that time it would be linear 45-degree line. So, we can easily locate this point and draw this line. Beyond this point, one has to find out, one has to pick up another point here and consider that to be SWF at that time. So, that using that as SWF, one has to draw a tangent, find out where it hits, find out what is SW bar, and find out where once you have SW bar, what is that SW bar minus SWI gives me the corresponding RP, and the slope of this line at that time, this is FW prime, and that FW prime is essentially 1 by Vp. Okay. This corresponds to the outlet saturation, such SW value at the outlet. So, from this FW prime, from looking at this slope, one can find out what is the Vp, and that Vp would be here, and the corresponding Rp would be SW bar minus SWI, and that Rp would be there. So, one can start locating these points one by one, take another value, draw a tangent, find out what is FW prime, find out what is Vp, and based on this see where it hits, get the SW bar, find out SW bar minus the SWI that you started with, and find out corresponding oil produced. So, Vp and Rp one can always find out from this exercise and locate these points one by one. Finding out FW prime would may be little difficult, because always see the focus here, though you are drawing this SW curve like this, but the focus here is beyond SWF. So, this part of the curve, this part is not, we are not interested in. So, this part if there is too much of a clutter, so what one can do is get the correlation of FW versus SW and analytically take the derivative, take analytically differentiate it, and then get the FW prime versus SW curve, and one can generate this curve of FW prime versus SW, and they put one just below the other. So, that this SWI corresponds to here this SWI, and this 1 minus SOR corresponds to this here. So, 1 minus SOR. So, the end point corresponds to here. So, and in between this is the curve of FW prime versus SW. So, any point we are looking at, let us say I pick up this point here. So, automatically we can drop it here and find out what is the corresponding f w prime. Okay. Similarly, any point there you can find out what is the corresponding f w prime. So, instead of going through this clutter, one can use this curve to generate the corresponding f w prime values, because you need f w prime values to calculate the V p. Okay. And you need S w bar anyway to calculate the, one has to find out the S w bar anyway to calculate the corresponding oil produced. So, this is one thing, and then if we look at the saturation profile, if we look at the saturation profile with respect to position, so we can see here this is where we started, that this is x equal to 0, this is x equal to L, inlet outlet, and then we see that the Buckley-Leverett front has travelled up to this location, and beyond this it was all at interstitial water saturation, because to start with entire porous plug was at interstitial saturation. So, now this, since the Buckley-Leverett front has travelled in, so water has gone in and increased the water saturation, but beyond this Buckley-Leverett front where water has not gone in any further, there the saturation is S w, that will remain as S w I. So, now here this we found out from this plot what is this is, I mean after you had a breakthrough, we can find out what is the corresponding S w f here. Okay. So, this is the value of S w f. So, since this is the value of S w f, so one can get this curve here, and then after that one can find out what is S w bar, and then one can find out what are the corresponding saturations that these values one can get, because we had already written, you may recall, that x is equal to L f w prime V p. So, from there at any location, for any saturation, let us say I pick up this is the front saturation, any other saturation which is higher, the corresponding f w prime I need to find out, we have to find out, and for the same V p is fixed. See, once we have, if this is the Buckley-Leverett front, when the Buckley-Leverett front reaches the outlet, that means this is S w f. So, that S w f is fixed. So, all saturations in the upstream side would be all saturations would be the greater than S w f. So, any packet you pick up, saturation packet, how far that will travel. So, you have to find out what is the corresponding S w f, and then one has to draw a tangent or use this curve to find out what is f w prime. So, corresponding f w prime one has to find out, but V p has to be, how do you get V p? V p is 1 by f w prime corresponding to this outlet saturation. Okay. So, that is the V p, but f w prime is corresponding to any other saturation, any other points you look at here. So, that is how one would look at, because when we freeze this particular saturation, let us say I am freezing this saturation profile here. So, that means this is the S w f. Okay. So, to achieve this S w f, what is the V p? V p would be, because then you would put x equal to L is equal to L f w prime V p, and this f w prime corresponds to this particular saturation packet which has reached the outlet. That means, this particular saturation packet for which x equal to L. So, basically this f w prime in this case. So, now from these I am calculating V p is equal to 1 by f w prime. So, that means, this f w prime is at the saturation at the outlet. So, first of all we have to pick up what is the saturation at the outlet. Let us say this is the saturation at the outlet. So, corresponding f w prime gives me this f w prime, but V p is obtained from sorry, what I said is these first you let us say this is the saturation at the outlet at any time. This is the saturation, let us say, at the outlet. So, for this particular saturation, one has to find out what is the corresponding F w prime. So, that from that F w prime, one has to find out what is the corresponding V p. So, that gives you the V p. So, and that V p goes in here. Now, if you pick up any other saturation, so that is the outlet saturation and the V p is frozen. Now, if you pick up any other saturation, intermediate saturation at intermediate location, so any other saturation you try to find out how much x that saturation packet will travel, you have to use this expression, and there the V p is already known, and F w prime you have to find out whatever saturation you are picking up. Let us say I am picking up this saturation. The outlet saturation is this much, but I am picking up this saturation and I am trying to find out how far it will travel. So, for that I have to then draw F w prime here or obtain F w prime from the graph for that particular saturation, and that will give me the F w prime. And once I know this F w prime for this saturation and V p for the outlet saturation at the outlet, then I take these, multiply this by L and I get x. So, I know that this saturation will travel as per this equation, this saturation will travel up to so and so distance. Similarly, pick up another saturation, find out how far it will travel, and one can create this profile. So, this is essentially the exercise one can take up from Buckley-Leverett form. So, what is written here is for any SW, greater than this SW at outlet, this SW we are referring to here. For any SW greater than this SW at outlet, calculate x equal to L F w prime V p, where F w prime corresponds to SW, V p is equal to 1 by F w prime corresponds to SW at the outlet. So, this is something which I mentioned just now. So, this is overall Buckley-Leverett form. So, if somebody gives you the relative permeability versus saturation curve, or if you have the instrument, I already explained the experimental procedure. So, if one does those, one can find out what are the relative permeability versus saturation curve. So, one can do this exercise, one can repeat these plots and get a meaningful result. So, this is all about this Buckley-Leverett form. Now, as I said that if we go to 3-phase flow, there would be another consideration which is known as PVT behavior. Okay. PVT behavior in the sense that if you have let us say this is the differential volume we are talking about, and out of that this is the pore space, and within this void this is the pore space and rest is solid, and within this pore space now we are sharing this pore space between oil, water and gas, 3 phases. Okay. So, generally water would be at the near the wall, it is most wetting, and then oil and then gas. So, they would be aligned in between, but they have good amount of mixing. One can expect that there would be an equilibrium between those phases. Why do you need an equilibrium there? Because this oil consists of, let us say if I look at a crude oil in a reservoir underground, this oil consists of several alkanes which starts from, I mean there will be some amount of dissolved gases. So, depending on the pressure. So, it is alkane means methane is CH4. So, then ethane 2 carbon and rest hydrogen. So, then you will have 3 carbon like this, and you will go to 3, 4, 5, 6, 10, 20, 30, 40 like this, you will go to higher alkanes. So, crude oil means it is a mixture of all these alkanes, and then there would be alkenes, there would be other components. So, now if you have, so these are these, now suppose I have a oil is, there is a natural gas also existing in that pore, then there would be, for example, natural gas would be primarily methane with some amount of ethane. So, there would be an equilibrium, so it will be a sharing. So, amount of ethane, for example, how much it goes to the gas phase and how much it will go to the liquid phase. So, there is a sharing. Okay, and it depends on pressure. If you reduce the pressure, then you find that lot of oil will go to the vapor phase. A lot of components go to the vapor phase, but if you increase the pressure, you will find those components again will go back to the liquid phase. So, there is an equilibrium, and it depends on pressure and temperature. So that is why this PVT behavior is important, and for this one needs to go to phase equilibria thermodynamics. This is basically you have a mixture here, and which one will go to the vapor phase by what amount and which one will remain. So, there would be a distribution coefficient of sort, and then that distribution coefficient depends on molecular interactions and all other fugacities and other terms. So basically it is a PVT relation, and it is basically it comes under the purview of phase equilibria thermodynamics. But when people are working in reservoir flow through a porous media in connection with reservoir modeling, there is a simpler way to handle things, and I thought I briefly touch upon that, at least just to give you a glimpse of what is followed there. It is basically the one can, instead of going to phase equilibria thermodynamics, and then one has to use thermodynamic relationships. For example, there are several ones available, say Uniquark, Unifac, Margules, Van Laar. Those are various activity coefficient models available, which can be utilized in this regard to find out how much go to the vapor phase and how much remains in the liquid phase. But instead of that, there is a more of empirical way of doing things, and which is in terms of formation volume factor. Okay, and the way this model is handled, I mean these are also, there is a name attached to it. Okay. So, now formation volume factor, the way it is defined is, it is written here, you can see V, let us say oil. See, there are two conditions specified. One is known as reservoir condition. Reservoir condition means we are talking about, let us say 50 atmosphere pressure, 90 degrees centigrade. I mean pressure and temperature, they are higher. And then we are talking about stock tank condition, which is more of like our standard condition, 25 degrees centigrade, 1 atmosphere. I mean that can be decided. I mean what stock tank condition one uses. So there are two conditions, and within these two conditions, as we switch from one condition to other, so naturally when it is in reservoir condition, there would be lot more gases which will remain in the dissolved state in the liquid, but the moment you bring it to the stock tank condition, those gases will flash out from the liquid. Okay. So, to account for how much will go to what state, for example, if I look at the simplest thing here, the formation volume factor for water. So, water here it is written VW, volume occupied by fixed mass of water under reservoir condition, divided by volume of that same mass of water under stock tank condition. So, if water has any compressibility, if water changes its volume, okay, because you have taken the pressure off, you have taken the temperature off. So, then this is the ratio, and this is known as formation volume factor for water, and this is considered function of PW. PO, we now, P is the pressure, we are now differentiating between PO, PW, PG, because we know that they may differ by capillary pressure and all. So, to remain on to remain consistent there, instead of function of pressure, it is in a function of pressure of the waiting phase, pressure of the water phase here, because water, oil, gas we are talking about. Similarly, here we can see for formation volume factor for the gas is same as Vg under reservoir condition to Vg under stock tank condition, and formation volume factor for oil, here we have VO plus VDG. VDG is the dissolved gas in reservoir condition, which will not be present in the stock tank condition. Okay. So, VO plus VDG at RC divided by VO STC. So, this is how it is, and further one goes to solution gas oil ratio, that is also another term RS in this regard, which is VDG by VO under stock tank condition, which is considered function of pressure. So, these are some of the terms one defines, and now they treat these that as if I have information a priori about what would be BO, BW, BG as a function of pressure, because if one knows all this, then one can draw continuity equation quickly. One can use this BO, BW, BG to draw the continuity equation without, but otherwise, I mean, if we had not known a priori this BO, BW, BG, then we have to go for the thermodynamic, I mean, we have to go to phase equilibria thermodynamics to find out how much would be the, what would be the volume of gas say at reservoir condition against what would be the volume of gas under stock tank condition. So, how much would be the expansion when I am changing the pressure from 50 atmosphere to 1 atmosphere, how much would be the expansion. But that, I mean, we have ways to do it. I mean, we have studied already in physical chemistry how it is to be done, but instead of relying or instead of going to those correlations, the idea here is to work with these parameters and now try to write continuity equation, because we have to write a continuity equation for oil. Because you remember our originally there was a continuity equation, then we said that okay, we can do this KRO, KRW, relative oil, relative permeability to oil, relative permeability to water, and use Darcy's law. So, that can give me, I can use Darcy's law with the relative permeability. So, relative permeability term. So, we can use Darcy's law. But now we have to at this time, I mean, Buckley-Leverett form, there we had, it was, the situation was much simpler. There we had only oil and water at interstitial saturation was present, and only water was injected. But now in this case we have 3 phases sitting there in the porous medium, 3 phases, oil, water and gas sitting there in the porous medium, and now I am having a flow, and maybe I have an withdrawal from some point. Okay, just when you generalize this, I mean, obviously there would be either injection or production of either oil phase or gas phase or water phase, either. So, one has to write a general equation, and so we have to write 3 continuity equation, mind it, one for the oil, other for the water and other for the gas. And obviously, there would be an accumulation term, and that accumulation term will only talk about SOSW, and for SOSW SG, in fact, you need only 2, because the other one would be 1 minus, say for example, if you do not know SG would be simply 1 minus SO minus SW, that is one thing, and how much would be the density change, but again the density change we are leaving it to this formation volume factor. Okay. So, now it would be challenging to see, now it would be interesting to see how these continuity equations play out. Now, we will write these continuity equations only instead of density terms. Now, we would express it in terms of density at some, I would say density at stock tank condition and use formation volume factor. So, by that way we can circumvent this problem of using a phase equilibria thermodynamics and going for a rigorous solution. So, this is something which I am going to cover in the next lecture. This is all I have as far as this module is concerned. Thank you very much.